Julian Canero, who is an MSc student in computer engineering at the University of Manitoba under the supervision of Dr. Ian Jeffrey and Dr. Jonathan Rigger, focusing on applied machine learning and signal processing. He is looking to improve data-driven analysis techniques used in industry by adapting some of those high-level mathematical approaches to the methodologies currently in use. Welcome, Julian.
Hey, just making sure, can everybody hear me?
Looks good.
Beautiful. Thank you very much for the introduction. Yeah, so we can get right into it. So I am here. Thank you for coming. My name is Julian, and I'm here on behalf of the University of Manitoba to present our paper, Characterizing Rail Corrugation through a Data-Driven Assessment of Impacts and Noise on Vibration. And as mentioned, this is a collaborative effort between the U of M, the National Research Council of Canada, as well as Advanced Rail Management. So to start off with, what is corrugation? Corrugation is the rippling or the presence of roughness on rail surface due to wear as a function of use. The point of contact where the wheel interacts with the rail causes a lot of impact and deterioration that manifests as corrugation at some resonant frequency of the system. It's on the scale of micrometers, but can actually be very detrimental to the function of the system, to both the rail and the vehicle. And there are some undesirable secondary effects caused by corrugation, which we've sort of focused on, specifically noise or sound, as well as vibration just experienced by the vehicle. So noise as a covariate is one of the primary motivations for rail grinding, which is how corrugation is remedied. It's dealt with by grinding the surface of the rail flat. However, it's done largely reactively as opposed to preventatively. So a particular transit system might grind through their entire, all of their rail in small sections across the duration of a year, meaning the corrugation can oftentimes be dealt with too late. We have been tasked with the development and validation of a measurement index to help with assessing the need to grind. And so in order to do that, we must understand the relationship between corrugation and its covariates, which we have specifically focused on noise thus far, to validate the effectiveness of a proposed index. So Magel and Oldno proposed an equivalent grinding index, which was meant to be a one-number summary for a section of rail as a weighted description of three major track condition metrics: the profile quality, or basically the shape of the railhead, the surface damage on the rail, and corrugation on the rail face. So our work focuses on what's called RCI sub 2018 or RCI 2018 validation and improvement, which lets us score or grade a particular section of rail. So currently, RCI 2018 was built on dividing sections of rail into blocks and assessing each block as a function of the root mean square calculation of the corrugation. RMS is just a standard for oscillating functions. You encounter it in electrical engineering as well for alternating current voltage. And so it's particularly adept when it comes to assessing oscillating or variable functions that normal mean doesn't capture quite properly. So this calculation focuses on specifically the filtered 30 to 100 millimeter wavelength band. And that is just sort of commonly where corrugation appears because of the aforementioned resonant frequencies in our system. TOL or tolerance was specified as 4 microns in their particular implementation, and each individual block in a longer section of track retained its own score independent from the others, which is nice because it gave granularity as far as the state of the rail, but makes it difficult to summarize an entire section. Advanced Rail Management has a similar segment-based index for their entire rail section. So this takes a measure of corrugation and basically reflects it on being representative of the entire section as a whole. So for a given, let's say 0.2 miles, which is roughly 320 meters, we have a section of corrugation that we filtered for the 30 to 100 millimeter band. We generate the RMS block value for each of the 5 meter blocks. So we wind up with about 64, give or take. Then a particular block value is chosen to represent the section based on its percentile in the distribution of the sample. Our work, so we focused on the 95th percentile value, which is basically the global maximum, but kind of throwing away outliers, or the 65th percentile, which skews a little bit more towards the median. This index has been referred to as RCIX or RCI sub X, where X is the block percentile of interest. So here we have an example where we have our 30 to 100 millimeter filtered section, which is being used to arrive at a measurement for RCI sub 95. This is collected with a corrugation analysis trolley mounted with accelerometers that is pushed by an operator down the length of track, and it samples the height of the rail every 1 to 2 millimeters. And we can see that the 95th percentile highlighted in red is moderately outlier resistant while still looking to explain the worst part of corrugation in this rail, and it ends up getting prescribed an RCI of 10.906 micron. So we did some investigation into RCI growth over one grinding cycle, so about a year in a particular property, across multiple sensor positions laterally on the rail face. And this was done for both tangent rail as well as curved geometries. And we were able to obtain data at 5 millimeter intervals laterally on the gauge face, starting from 25, which is gauge side, all the way up to 40 millimeters, as set in 5 millimeter increments. So for reference, the 35 millimeter sensor is the tangent running band. And then as we move to non-tangent, that slides based on whether you're the low rail or the high rail to 40 millimeters or 30. So what we found was that we could see consistent RCI 95 growth in the 30 to 40 millimeter sensor positions, 35 inclusive, in both tangent and non-tangent rail, while 25 millimeters saw very, very little growth. We found that the correlation coefficients when doing this, in tangent rail, we saw growth with correlation coefficients between 0.85 and 0.98, so rather strong linear correlation in their growth, as you can see in the two plots below here. And with non-tangent rail, in those same 30 to 40 millimeter windows, we saw R-squared values between 0.56 and 0.96. That 0.56 was a bit of an outlier. The other three were above 0.7. So we determined that RCI is actually sensitive to growth in a reliable way, which going forward can hopefully be parlayed into usability as an index. We obtained our data from a Canadian rail property, and this allowed us to easily perform geometry-based analysis, as we just saw. This site gives corrugation samples sampled by the corrugation analysis trolley, as well as wayside noise measured at the tangent and non-tangent segments of the rail, just with a microphone located near sort of the side of the train. Or side of the rail, rather. It's difficult to look at corrugation in a vacuum. We felt that we needed more information for our decision making. So sound and noise being a common issue due to impact to health and safety from prolonged exposure to noise for people in the immediate area, not just riders, but also as well as rider comfort, obviously. That made it a very good covariate to look at. It's easy to measure passively, either on board or wayside with minimal use or impact. And ideally, we can find some insight into noise growth that can be perhaps predictive or indicative of corrugation, aiding in decision making. So we used wayside noise, as mentioned, taken near the track in the middle of the curve and tangent sections of this test site. Obviously, it's not continuous noise, it's sort of variable. So what happened was there needs to be some math applied to boil it down to a single number or a multitude of single numbers representing different frequencies. So this was done with the equivalent level sound or time average sound level, which gives us a spectrum of decibels for the different standard noise frequencies that we're expecting to look at that would have consistent or equivalent mathematical power as our variable input noise that we just sampled. A weighting is applied to this to properly highlight or amplify human noise sensitivity. We're sensitive to 2K to 5 kilohertz. So this adequately amplifies 1 to 6K. And just visualizing it here, you can see it's not quite a transfer function, but you can see that there's a gain above 0 decibels between 1K and about 6K, indicating that those are amplified as opposed to outside of that range where it is dampened. So what we have here is a sample table of our data. So for measuring usage, due to COVID, when we were doing this all through 2020, it made date a little bit unreliable as far as an approximation or as far as an independent variable to use. So we use million gross tons or MGT experience and then sort of estimated that based on what we could learn about the ridership at the site. The RCI for the 95th and 65th percentiles on the left and the right rail are present, as well as our average LAEQ and the 95th and 65th percentile values. Standard deviation also makes an appearance, but it's not particularly relevant to this work. And track type allowed us to filter our data according to geometry. So we wanted to look at some of the relationships between these values. So we generated a correlation matrix where each cell in this matrix is the correlation between two particular columns, in this case filtered for just tangent rail. So this tells us how strong the linear relationship between the two is. And I want to draw your attention to the two black boxes in the bottom left and right, top right corner, which shows very high correlations between all of our RCI values and the LAEQ values, which is really nice. This is desirable. We can see these strong positive correlations. So ideally, there is some sort of link there. Similarly, looking at it filtered for curve, it's similar, but it's a little bit less strong. There's significantly stronger presence in the right rail, which is our low rail. So some sense can be made there because of how curves work. The train is not traveling fast enough. You will see stronger impact on the low rail as opposed to the high rail because you don't have centripetal force sort of pushing it outwards. So at least numerically, there was enough here to believe that there is a tangible relationship that we can look through. So these were validated in the plots. So what we have here is in red, our RCI for the 65th and 95th percentiles in red, and the LAEQ versus MGT in blue. And so we see this is pristine. We can see very similar growth in all 5 of our trends, obviously the 65th percentile at a smaller slope, and then a very strong response to grinding mirrored in all 5 lines. So this was great. It's what we wanted to see. Looking at the right rail, we see an interesting sort of concave up growth, not purely linear. It looks to get worse over time, indicating that maybe corrugation begets corrugation, the idea that it's a positive feedback loop. And so we see that there's a less pronounced 65th percentile growth, which sort of shows just based on relative to the 95th that the high or the worse corrugation is actually growing at a faster rate than the average corrugation, something worth noting, or not average, more median, I should say. Looking at our curve noise, curve growth, what we found is that the RCI in the high rail does not grow particularly well at all. It's not very intuitive. And so there were some questions concerning that, but as we reviewed, we realized, yeah, it's the high rail. There's a very good chance that it's just not seeing the same impact of forces as on the tangent or on the low rail. We can still see that there's the response after grinding, which is good. That's really all that we're focused on with this one. And then looking at the low rail, we can see, again, that sort of concave up growth in the RCI, and we see very good responsiveness to grinding. So we're very happy with all 4 of those plots and how numerically it's justified. So our proposed effectiveness to justify or validate RCI sub X is given a sample noise of corrugation and some amount of desired reduction to a particular level. We want to assess pre and post grind measurements for noise and sound. So for instance, if we have our tan rail at 100.6 dB and our target is 86 dB based on the BC Health Authority, we have a noise nuisance that is shooting for 14.6 dB, understandably. And that can be mirrored for corrugation. Once we have our absolute and our desired difference, it's simply just a ratio of the two, sort of implicitly capped between 0% and 100%, as effectiveness can't be more than 100 or less than 0% effective. And using these, we can basically assess how RCI performed. So based on this table, we can indicate a reasonableness of our proposed effectiveness and that RCI responds as we would hope. So it shows a good response to grinding, visible in multiple percentile values and the mean values for specifically LAEQ. And it gives leniency based on how stringent or lax our desired thresholds are, which is good because it can be variable from property to property if they choose to use this. Based on this, we feel actually very strongly about our work thus far with the proposed RCI sub X. And going forward, we can, now that we have some sort of validation for it, we can actually look at determining thresholds that will dictate when we would use it. So to recap, we proposed RCI sub X as an index. We have provided some initial validation steps that have shown promising results as far as how accurate it is at representing the rail. We found that it accurately mirrors noise as a covariate and shows appropriate responsiveness to grinding, which is something that we were interested in. Our continuation will involve some decision-making on particularly valuable thresholds and parameters to finalize actually scoring with this index to provide a concrete answer as to the condition of the rail. And in addition to this, we'll be replicating our work on new grind cycles at the property that we used, as well as repeating work on a different property. Lastly, we're looking to replicate some of this relationship work with onboard accelerometer data to take a look at vibration as a covariate as opposed to noise to see what we can learn from that. Just a few acknowledgements. We would like to thank National Research Council for their help with this, as well as Advanced Rail Management and the people linked to this project. And that is really all that I have. I guess if we have time for questions, I will take some.
Indeed we do. So if there are any questions for Julian, please feel free to either type them in or put your hand up. Thanks so much for that presentation, Julian.
Thank you. Thank you for having me.
Yeah, no worries.